for coming. And as we found out, this is so I'm going to define the exact same set of polynomials that June just talked about, and coming from a somewhat different perspective. So one of the nice things I think about this whole sort of story is that it has been approached in a lot of different ways for a lot of different reasons, and the same sort of set of polynomials the same sort of objects have come out of all of them, and so let's talk about those. So just to repeat some things, so if I have a polynomial, non-negative coefficients, I'm going to say it's log-concave. Log-concave.
Can you change to a black?
Sure. Is okay. Let's try again. Oh, this is a bad black one. Well, is blue readable? Yeah. Okay. Let's use blue. We have polynomial non-negative coefficients. Say it's log-concave. On the positive orthant. If, as a function from the positive orthant to R, it's concave. The log of it is concave. So f is automatically non-negative. It's positive on the positive orthant if it's a non-zero polynomial, and so we want log of f. It's a function from the positive orthant, real numbers is concave. And I'm just going to include, because it's a little bit easier to do, I'm going to call the zero polynomial log concave, even though we should not take the log of it. Let's just put that in there. And then we're going to say that f is completely log concave. If not only does f have this property, but whenever you take any directional derivatives in positive directions, you get a polynomial with this property. So if so pick k vectors. And concave. Positive orthant. For any non-negative vectors. E1, k, and a non-negative orthant. And here what I mean by this differential operator is exactly this. So I'm going to use the same notation for differentiation with respect to a variable. And what I'm going to do is I'm going to pick a vector. Here my vector is going to be non-negative, and I'm just going to take the directional derivative in that direction. And so this is the property that I would like to explore. And a priori, we just saw sort of many examples, but a priori, it's not clear that any polynomials sort of fall into this category. But a very sort of quick example is if you take a univariate real polynomial. So univariate with the roots non-positive, so Ri non-negative. And then there's not so many choices for there's only one direction to go in, so we don't have to worry about any of this direction nonsense. And if we try and test whether or not it's log concave, we take log. We do the not even multivariable, just single variable calculus problem, and we take the second derivative of log, and what we get. So log of a product is a sum. Sum of 1 over all of these things. You take the derivative again, and what you get is minus 1 over x plus squared, which is going to be negative for every real number that I plug in. And so that means that the log is concave. One of the big motivations for this story, I think from our perspective at least, is a multivariable generalization of real rootedness called stability, which we've already heard a lot about during this week. So another big example is polynomials that are stable with non-negative coefficients. Where one definition of stability, just in case anyone hasn't seen it, is that if I take any univariate restriction, I want this to be real rooted whenever I walk in a positive direction. So for all vectors v in a non-negative direction, and I can start from any point. The picture, I like to have in mind for this, you could draw the zero set of a stable polynomial in 2 variables. And if it has degree 3, maybe we would find something like this. So this is a set of points where this polynomial is 0. And if I restrict to any line in the positive direction, I will find 3 real roots of this polynomial. And sort of for the same reason, such polynomials are, the log is concave on the non-negative plane. And it's interesting because these were studied sort of first by a very related class of polynomials called hyperbolic polynomials were studied by Garding for PDEs, and he actually showed that the log is concave on sort of this region. So it has sort of a interesting history that way. And so these are log concave, and if you take any derivative, just like if you take any derivative of a real rooted polynomial, you get a real rooted polynomial. And so the same argument will go through. If you take any multivariate polynomial and you take one of these directional derivatives, just sort of like taking, which is the same as taking the derivative with respect to t of this polynomial, then you get another stable polynomial. And in fact, the zero set will interlace. So here we'll get. This might be the zero set. And so putting those 2 facts together shows that any stable polynomial sort of satisfies this property. Let's leave that in. And the thing I want to start off with is part of this long list of equivalent conditions that was just written down. So far, if you have a homogeneous polynomial, non-negative coefficients, write down the same list and add a few things. So The first is that f is completely log concave. I'll abbreviate this. C. The other, so we can go down the list, right? So f is strongly log concave, which we saw a definition of in June's talk. And f is Lorentzian, which we saw a definition of in June's talk. And there's a few other that I want to add to this list. One is that so as we saw sort of here, the thing that's important is quadratics. Like that's sort of where all the action is happening. And that's true even if you allow yourself vectors in any directions. So it's not too hard to check that if you're taking directional derivatives, the ones that really matter are when you take as many as you can. So this is log concave. And then the last one is sort of a two-part condition, which is, I think, analogous to the sort of analogous to the two-part condition we saw before, but I'm going to write down slightly differently, which is that one, whenever you take derivatives really in the coordinate directions, so it is log concave. Whenever you take exactly d minus 2 derivatives, this is exactly the same condition we saw before. And then the other that I want to write down is that this is, whenever you take a directional derivative, you get something I'm going to call indecomposable. Rho alpha less than or equal to d. Where the thing that I want to, where indecomposable is avoiding this type of polynomial we saw before, where it's really a sum of polynomials in two different sets of variables. That's trouble. So we want to avoid those. Any questions before I start erasing anything?
By the way, for the terminology, that word is already occupied in decomposable for the product of polynomial with separated variables.
If you have a better word, from Markov chains, the natural word is irreducible, but I refuse to change the definition of irreducible for a polynomial.
This, in this context, was the definition was used for.
I see. Well,
but anyway.
If you have okay, open to changing such a name. So this is really just f does not equal the sum of two polynomials, non-zero polynomials where g is in one set of coordinates and h is in some other set of variables. That's what I want to avoid. For this talk, I'm going to call them indecomposable. Other questions? So I want to go through a few sort of interesting cases, and the first, just like we saw earlier today, is to think about quadratics. So if I have some polynomial in n variables, it's quadratic, I can write it as a real symmetric matrix. Maybe I'll put a half for x. And then if I do the natural thing, which is to take the Hessian of a log of f, if you actually do it out, this is the multivariable calculus exercise. Then this is f times the Hessian minus the rank 1 matrix we get from taking outer products of the gradient, and then you divide by an f squared. Maybe I'll put an f squared over here because we don't want to worry about it. In this matrix, this is a matrix. This is really Q. We take a quadratic polynomial, we take the Hessian, we just get this is, the representing matrix. And the way that I would, and so this has to be negative semi-definite when we evaluate at any point in the non-negative ordinate. And of course, Q doesn't. So what depends on the actual evaluating at a point? F changes as F varies with the point. This is just a constant matrix, and this changes a bit. Right? But the way that I think it's best to read this is that we have a quadratic form, and when we're subtracting off a rank 1 matrix, we have a quadratic form with non-negative entries. And we're subtracting off a rank 1 matrix to make it negative semi-definite. So in fact, this function is negative semi-definite on the orthogonal complement of whatever this vector is. If we evaluate it at such a point where this doesn't matter, we need to get something negative semi-definite. And again, the picture that I want to have in mind for this is, so this polynomial, because the entries of this are non-negative, it necessarily is going to take positive values on the non-negative orthant. And what this condition says is that there's some linear space on which it's negative semi-definite. Q positive. And Q must be negative. And so then in between, it really should be 0. So this is not a great picture because, and so what really has to happen is that this quadratic polynomial has to be stable. If I'm doing homogeneous, the honest picture here is really 2 straight lines. Bigger picture, the 3D picture, which is harder to draw. I want the 0 set of Q to look like a column. It's going to be negative semi-definite on some linear space. Little q is f. And so we said before that every stable polynomial has this property, and for homogeneous quadratics, it's really the same. It's nice. It's not the same in general, as a spoiler. But for quadratics, it's really the same thing. So just to do a tiny example, if we had a bivariate quadratic, two variables, a2 x squared plus a1 xy plus a0 x squared. This is completely log-concave if and only if the Hessian one has the determinant less than or equal to 0, right, which will give us the usual sort of discriminant for a degree 2 polynomial. And if we jump down to this, then we recover something that I think was also in Leonid's paper, which was that if you have a polynomial of degree n, two variables, then this polynomial has this property, if and only if. So let's write down this condition really just translates to support the fact that the support, the set of k's where ak is non-zero, is an interval. There's no gaps. So it's consecutive. And all of the things you can get by taking derivatives of this down to a quadratic gives you a quadratic of this form. And the determinant and all of the Hessians, so I can take the derivative with respect to x sometimes and the derivative with respect to y sometimes. Is non-negative. So every sort of triple of consecutive coefficients, I'm going to get some inequality. And as we saw, these inequalities are really nice, which translates to exactly these inequalities that the coefficients are ultra log concave. So this is you can homework exercise. Is that if you take all of these, if you take derivatives to get down to a quadratic, and you take the determinant of this little 2 by 2 matrix, you get a bunch of inequalities that look like this. And so here, we really see already there's a difference between sort of real stable. So this polynomial is stable if and only if sort of the univariate polynomial is real rooted. The real polynomial you get by restricting y to 1 is real rooted. That's the condition for stability, which implies these inequalities on the coefficients, but is not equivalent to these inequalities on the coefficients. So we really get something stronger than stability. Yeah. Sorry?
The consecutive coefficient which over 0, this thing is equivalent. What do we have?
So the pair So these should go together. You need both.
By the way, there is a way kind of to say in one statement. So instead of writing those Newton inequalities, write that ratios are monotonically decreasing, corresponding ratio. Then it immediately would imply. This is actually how I do.
Okay. Well, I mean, I like this both because it,
Because of that in the causability.
As an illustration, what would happen if it was not consecutive? If there was a gap, then you take derivatives to isolate the left side of the gap and the right side of the gap, and you're going to get something that looks like x to the something and then y to the something with nothing in between. And that you can write as a sum of two polynomials in separate variables. Okay. I want to talk. I want to basically just. I'm not going to sketch a proof of any of these things, but I want to just talk about sort of one or two pieces that I find nice that are involved in this, and that people who care about stable polynomials and interlacing families might care about. And one is one question you could ask about such polynomials is when can you add them and preserve this property? Again, so a lot of this is sort of inspired by the theory of stable polynomials, which we've heard a lot about this week. And if you have two stable polynomials or two real-rooted polynomials and you want to add them and get something real-rooted out, then it's very convenient to have a common interlacer to be able to sort of separate the roots of these polynomials into intervals. And I think it'd be very interesting to develop an analog of this story for these polynomials. And the closest that here's a baby step towards doing that is suppose you have two polynomials. Of the same degree, and they have a common derivative. Which is non-zero. Some vectors VW. Some non-negative vectors D and W. Then I claim these are completely log-concave, and they have a common derivative. Then I claim the sum is completely log-concave. And the idea is really that when you get down to taking derivatives and getting down to quadratics, they're going to have a common interlacer here in this picture. So E of U1 namely dv of this and dw of this. And so really you have two quadratics. They're both positive on the positive orthant. They're both negative on some linear space. And so when you add them together, those properties are preserved. have to make some argument to say if you know it for quadratics, then you know it for everything, but that's not too bad. And so the question, so we saw all this stuff about interlacing, there's all this useful stuff for stable polynomials, and the question for pretty much everything I write down is like, what is there an analog for every theorem about stable polynomials? You want to ask, like, is there some good analogy for this? And so there's lots of people active this semester. I think trying to understand what the set of interlacers are of these polynomials would be a very interesting sort of interlacers. Completely log-concave bond.
Cynthia, before you erase, I'm still puzzled by this consideration. If you look at vectors orthogonal to the gradient of f, your point x will be, forming the quadratic form out of q, so you'll get x transpose qx, but there is another x transpose qx coming out of f. So how do you actually get negative?
Let's do it, actually, because it's sort of...
It seems to just square your relation, and this is not what you want. Let's do it.
Okay, so f, there's going to be constants that might go wrong, but let's ignore them. So f is, so I'm going to evaluate at some point. F, there's its Hessian, and then this is like... That's my matrix. And I want this to be
Ready to sign it.
Yeah, I'm going to ignore this for a moment. That's okay. There's constants, they don't end up mattering. Okay, but let's I want this to be negative for all choices of B.
No transpose.
Oh, yeah. Okay.
The first.
This one, okay, right. And one sort of fact I really like is this is actually the determinant. This matrix. I want this always to be negative. And this is really, what is this doing to Q? This is restricting it to a two-dimensional linear space. That's this matrix. And so this says I restrict Q, the quadratic form Q, to any two-dimensional linear space. It's still going to have, this is non-negative, or this is really positive. This is some positive number. So the matrix is not going to be negative. There's going to be at least one positive eigenvalue. And this is saying that there's also a negative eigenvalue, or not, or 0. And so this is saying for every, you take some vector in the positive direction, you take any other vector, B, and you restrict to this linear space, you get an indefinite quadratic form. And we can really translate that to, this happens. if and only if Q is negative. Is negative semi-definite. On a linear space of linear space. Dimension n-1. Then whenever you take a two-dimensional linear space, you're going to intersect this, and you're going to get a negative. What was your original question again, Olga?
We can take it offline.
Okay. It is possible. It seems weird because you have this matrix with non-negative entries, and many of its eigenvalues are negative. All but one of its eigenvalues are negative.
No, that doesn't bother me. First of all, there were no assumptions on Q initially stated, so that's part of my confusion.
I see, non-negative entries. Other questions before you erase them? And so what this means is it lets you sort of move around the vectors in these derivatives. And in particular, you can sort of deform these vectors to the unit vectors in order to get really derivatives with respect to the variables.
I'm sorry, is this how you prove the equivalence, right?
Yeah.
So it's basically the main moving part is that idea, right?
Yeah. Yeah, it's really just get it down to quadratic form. You get down to sort of the quadratic case, and then you can move these around. And this indecomposable, so this, okay, the other claim is that if you have derivatives that are completely log-concave for all I, and f has this property, then f is completely log-concave. So step prove it, or let's even do directional derivatives are completely log-concave for all vectors. And again, the idea is that derivatives have a natural common interlacer. Namely, you take the derivative with respect to both of them. And so long as this is non-zero, this is going to allow you to take sort of non-negative combinations of these. Kind of bootleg up from. But it's a long sort of laundry list of all of these things, but all of the arguments are really what happens to quadratic forms and then like basic computations on polynomials. Okay. And one of the things that are very nice about these polynomials, or maybe I'll start with one of the things that always sort of bugged me about stable polynomials. Stable polynomials are beautiful. We love them. There's this nice theorem. Shall we? Wagner that if you have a multi-affine polynomial, and maybe it's homogeneous, so with non-negative coefficients, if this is stable, then the support, the set of subsets for which this coefficient is not equal to 0, that these are the bases of some matroid. This is a theorem that I like a lot. And you can ask, the natural question is, well, for an example, so for example, the elementary symmetric polynomials are beautiful, stable polynomials. So you can get up to a constant by taking the directional derivative of just the product of the variables. Beautiful stable polynomial. And what I mean by support is I take, well, x1, x2 shows up with non-zero coefficient, x1, x3 shows up with non-zero coefficient, x2, x3 shows up with non-zero coefficient, and the corresponding matroid is the uniform matroid of rank 2 on 3 elements. So there's also this sort of combinatorial structure showing up in stable polynomials, but not all matroids come this way. So Peter, Brendan, showed that sort of not all matroids come this way. Explicitly, the Fano matroid is not the support of any stable polynomial, and there's many others. And it's a little bit of a mess, like which ones show up and which one doesn't. I always find this a little bit sad, because I like stable polynomials and I like matroids, and you'd want them to have a tighter connection. And so for me, one of the big selling points of this generalization is that it really captures matroidalness, which is exactly what June talked about. And so one of the theorems that that he wrote down for more general jump systems is if you have any matroid, then the basis generating polynomial is completely log-concave. So you sum for all the bases, product. In basis, this is completely log-concave. And so this really captures, so not only is the analog of this statement true, if you have any coefficients that make your polynomial completely log-concave or Lorentzian, then its support are the bases of some matroid, but you can take the coefficients all to be 1. And so this is one of the nice sort of polynomials on the boundary that we saw in this open set. And if you want to, for example, get inequalities on the number of independent sets of a matroid, it's nice to know that you sum over all of the independent sets. To take sort of a modernization of the independent set polynomial. This is also
Completely log-concave.
which you can check. And you can check by using sort of these two, any one of these things, right? This, and some of them are easier than others. I think this one is, one can check, and it's sort of the same calculation as checking that these are. So what you do is you can, in decomposability, maybe it corresponds to some thing about the support of matroid polynomials, and then log concavity you can check by really just taking derivatives to get to a quadratic. And another fun sort of homework exercise is to take polynomials like this and see what differentiation does in terms of the corresponding matroid. So, and one of the one piece of this story is that for real stable polynomials, as we've seen throughout the week, if you have a stable polynomial, you can think of it as a probability measure given by the coefficients, and then you can go to town on using approximation algorithms for that, using that probability distribution. So my co-authors, Nima and Cheyenne, have been doing this with a lot of stable, doing this for stable polynomials, and they had the same sort of frustration that, you want to talk about all matroids, but it's difficult to get a handle on all matroids. And so one of the pieces of this puzzle is that we've sort of been, all of the stuff that works for stable polynomials we've been trying to extend to this story. So explicitly, we wanted to talk about probability distributions. Take some probability distribution on subsets of 1 through n. And I could write down its generating polynomial, which will be nice multi-affine polynomial whose coefficients come from the probabilities. If this is an honest probability distribution, note that when I plug in the all ones vector, I get 1. Summing up over the probabilities of all those sets. And then so we've seen a lot this week. Strongly Rayleigh distributions. Which are really just distributions so that this generating polynomial is stable. And so the analogous thing to do is to put down the condition that this generating polynomial is completely log-concave. We're lazy with our terminology, we could just say it's completely log-concave.
homogenize this GMU?
I do not, although most of the examples we've considered have been homogeneous. I should say, you could also, so this definition that I wrote down of complete log concavity didn't require homogeneity. You could also do it for inhomogeneous polynomials. And one of the things that seems to be true is if you have an inhomogeneous polynomial with this property, complete log concavity, then you can sort of homogenize it in a scaled way and get a homogeneous one. If you have some polynomial and you write it as a sum of its sort of homogeneous parts. So if you have some polynomial, then f is completely log concave, if and only if a sort of weighted homogenization. So there's also sort of a non-homogeneous version of all of this stuff. We haven't found, I don't think we have any good applications of it, but it's sort of out there and would be interesting to understand better. Yeah, so a priori, this doesn't need to be supported on only sets of size d. It could be supported on anything. And so, so one thing that one might want to do, given access to such a distribution, is to sample from it. For example, we might want to pick bases from a matroid, or count the number of bases of a matroid. One of the things that Nima and Cheyenne sort of had built up is that for, or probably many people in the room had built up, is that for strongly Rayleigh measures, you can do all of these things effectively. You can do good sort of approximations to these measures and to counts of their supports, and they're nice to work with. And so part of the thing we're trying to build up is to do the same thing for these measures. I'll give the super short version of what I was going to say. So if I'll give the super short and bad version of what I was going to say is that one can approximate, for example, the size of the support of such a measure well using a convex program.
What is n?
Sorry. So the number of subsets such that mu of s is not equal to 0. For example, if you took the uniform distribution over the bases of a matroid, this would just give you the number of bases. And what Quickly we'll talk about tomorrow is that you can also sort of define a Markov chain on the support of these things that mixes quickly. So come back tomorrow morning for Quickly's talk. And in the few minutes remaining, since we to sort of have everyone in the room. I wanted to sort of present a question to the crowd, which was that all of this sort of started, for me at least, this all started by seeing June talk about Hodge-Riemann relations on things and translating it into things about polynomials. So sort of a fancy way of writing down the definition of complete log concavity is that a certain quadratic form of Rn to R, which eats a vector and spits out the following number. If you pick some vectors, v1 through vd minus 1, this is a differential operator of degree d. This is a polynomial, homogeneous of degree d. This will spit out a number. This is negative semi-definite. On the kernel of some linear map, namely the one that eats w and spits out another number, where for all choices are vectors in the non-negative orthant. Convince yourself that this is a linear space. This is a quadratic form. That's the sort of statement. And if you, modulo sort of replacing negative semi-definite with negative definite, this is the mixed Hodge-Riemann relations at sort of the first level. There's a lot of them, and this is sort of level 1. And I think a lot of nice things sort of came out of level 1, and it would be really cool to try and, or one of the things that I was sort of curious about and have no answer to is what the higher ones look like. So Q. We might instead consider the condition that the quadratic form that eats a polynomial differential operator, homogeneous of degree q, spits out a real number. That comes in. Intuition for these, I encourage you to ask June and Kareem, who are in the audience. That this is negative semi-definite. On the kernel of some map. Vectors. This is the vectors in the non-negative orthant. I hope this is an adequate translation of the higher degree ones. And as far as I know, this property is not terribly. This class of polynomial satisfying this is not understood. I don't think it's even known if stable polynomials sort of fall in to satisfy this. June might be.
Can I make
Yeah,
a comment? So I tried that.
yeah. Okay.
And it turns out that that's not the right notion. So
Oh, no.
even stable polynomials do not have that property.
Oh.
So the problem from geometric point of view is that, I mean, it's not so simple. So that, in order for that formulation to work, the variety that you have secretly in your mind has to be sort of a smooth. And the reason why that property fails for stable polynomials is that often the case, the ring that's behind your polynomial f
Yeah.
is not the ring that satisfies the Hodge-Riemann relation. So in this formulation, the homology ring that you have secretly in mind is like a polynomial ring modulo the annihilator.
Yeah. Yeah.
That's not the right ring.
That's not the right ring.
That's not the right
Oh, no.
ring. That ring, you're sort of forcing Poincare duality, but the ring you actually want is not that one. And actually, it's a fun exercise to come up with a counterexample to that statement for stable polynomials.
Harder exercise. Great. Is there a right ring?
There should exist a right ring, but it's not as... Yeah.
Wow. Okay. So,
I have a question.
yeah.
So I was thinking a little bit about this. What about this definition? Maybe it's again wrong. So what you do here, the strongly log-concave, you differentiate n minus 2 times, and you get to a stable polynomial of degree 2. What about you differentiate n minus 3 times, and you get to stable polynomial of degree 3?
Yeah, that may be more interesting.
Okay,
than this
and the reason is why I was thinking about that. It's actually, so my interest to all this stuff was proving lower bounds on the coefficients, was van der Waals and 6. And actually there is a big difference between stable, you get different constants there. So, but if you on that level get this, if you get stability, you get better constants, okay? So this would be the definition.
That's a question that makes sense.
Yeah.
So it could be like K level, okay, so you just get to the sum. Differentiate n minus k times, you get, K step.
Any other quick questions? Great. Okay, let's thank Cynthia again. Coffee break, the next talk is at 11:45.